Does that sound loud when Zoom speaks like that? Okay, sorry about that. I meant to look into that setting in Zoom. All right, so difference in population means. There are two different cases that come up when we're looking at two populations. One is that the two populations are independent. Versus matched pairs. So independent would be something like that. Those mice, you know, some of them were in the light all the time and others had a regular light dark cycle. Those were two different groups of mices. So those would be independent. A matched pair would be something like the difference in a husband's and wife's age because they're a couple. So we take, you know, the male and the female from the same couple and we subtract those numbers before we find the mean. So it's kind of an order of operations things. With the independents, what we do is first we find the means, and then second we find the difference in means. With the matched pairs, because they're couples, or maybe even the same person, right? So it could be me, my pulse rate while I'm teaching class versus my pulse rate when I'm trying to talk to the board of directors of the college. Is my pulse rate different when I'm talking to you guys than when I'm talking to them? Probably. So in that case, I would just look at my pulse rate, and I would look at, you know, another person's, and they're all matched because it's the before and after kind of thing. So the order of operations here with the matched pairs is first we find the differences in the numbers. And then after we get all those differences, then second, we find the mean of the differences. So anytime we have two populations with means come up, we got to ask ourselves, are these two populations independent or are they stuck together? And there's a different procedure for each. So the procedure where they're independent, different, that's covered in section 6.4. So we're going to do that right now. And then we've actually been doing the 6.5 stuff since we started this. So 6.5 is really kind of a review. So we'll do that one second there. So I'm going to bring up a new page. So to be more clear, what we're looking at now is a difference in means. For two independent populations. So once I've got that, then I say, okay, now am I doing a confidence interval or am I doing a hypothesis test? So I'm going to do the confidence interval on this side and do kind of like I did before. And then we'll separate that from hypothesis test, and we'll do a couple of each. So confidence interval, we need to know several things. The most important is the standard error, SE. And it's a tweak on the standard error we used to have. Before, we would say, take the sample standard deviation and divide by the square root of the sample size. But now I have two things to look at how they're spread out. And so we have to add their spreads together. And the way we do that is inside the square root, we have the standard deviation of the first population or sample squared divided by its sample size. And again, all of this is inside the root. And then the standard deviation of the second sample squared divided by its sample size. And just a reminder of how that's related to the previous one is if you think about, well, what if they're the same? Then I would have s squared over n inside the square root, and the square root of a square cancels in the numerator, so I get just s in the top, but I'm still taking the square root of n. So that's kind of how this is related to what we were doing before. And this is a pooled standard error, that's what they call it. Other things to think about here, this is now a mean that I'm working with. And when I work with means, I have to use a t distribution. So I have to find what's called t star. And we've been finding t star either in StatKey or in a spreadsheet. And the spreadsheet formula for t star is the t dot inverse of the value we call alpha over 2, comma, and then the degrees of freedom. There are several ways to calculate degrees of freedom for two samples. There's what's called a pooled degrees of freedom, which is this insane formula. I'm not going to do that. The book doesn't do it either. So we're going to use this simple version of degrees of freedom. And it's just to take the minimum, the lower of either the first sample size minus 1 or the second sample size minus 1, whichever one's smaller is what we take for the degrees of freedom there. The alpha over 2, reminder of where that comes from, once we choose a confidence level, then we're saying what the middle of our spread should look like maybe 95% in the middle. So that's the confidence level goes in the middle here. The tails have to split what's left over. So that's what we call alpha, is in the tails. So that's 1 minus the confidence level. And then again, since the tails have to split that, then that means each tail here gets an alpha over 2 for what ends up in its tail. And we've done that before. We've been given the confidence level, we find out what's left over for the tails, and then we cut it in half. And so that's the percent that goes here for the t-value. Now, when we do that, alpha over 2, this inverse is always looking at the left tail. For t-scores, t equals 0 is in the middle. That means this t-score over here is going to be negative. So I usually in the formula take the opposite. You might remember seeing me do that before. So I take the opposite of the t inverse of the left tail probability based on the confidence level, and then degrees of freedom here is going to be the smaller of those two numbers. Once I have that, then the confidence interval comes from the following formula, kind of like before. So generally for a confidence interval, we take whatever our sample statistic is, that's the middle of our interval, and then we add or subtract the z or t-score. This time it's a t-score, we call t star, and we multiply that by the standard error. And this number that we're adding and subtracting here, that's our margin of error. So this is always what a confidence interval looks like. The sample stat here is going to be the difference in the means. So that would be x1 bar minus x2 bar, and then we add or subtract that magic t-score times that crazy standard error formula. And once we enter something like this in a spreadsheet, we can just keep reusing it. And so my hope is you've been trying to reuse the spreadsheets I've been creating here to make this a little bit easier. Confidence interval, difference in two means. Hypothesis test isn't too different. For a hypothesis test, we need a null hypothesis because we need the null value for that. So the hypothesis test, typically we're going to say that there isn't a difference in means, right? We're going to say that they're equal to each other. So mu1, population mean, mu2, second population mean, they're the same. Remember, the alternative version of that is if we subtract the mu2 over, mu1 minus mu2 equals 0, right? There's no difference is what we're saying, right? They're the same. Same, no difference. The alternative is that there is a difference, they're not equal, or one's bigger or smaller than the other. So I'm not going to write down those three alternatives right now, but this is important here because this right there is my null value. So when we look at a difference, generally we assume the difference is 0. So that's the null value. Because to actually take the test, I need a T-score. So what's called a standardized test statistic. Standardized test statistic. And the standardized test statistic in this case, because it's a mean, is a T-score. T is a kind of Z, but it's a little bit different. And a T-score is always the sample statistic minus the null value over standard error. Right, so that's the kind of generic form. We've done that over and over again. And that looks like a minus there. It's not a minus there. Sample stat. So in this case, the sample stat, that's the same thing down here. That's going to be our x1 bar, the mean from the first sample minus the mean from the second sample. Value for the null is 0. Subtracting 0 is kind of lame. You don't have to do anything there, but I'm going to write it in anyway. And then the standard error is the same standard error from over here. So unlike proportions where the standard error is slightly different, for the means it's the same. So that is our T statistic, our test statistic. So that gives us how many standard deviations are we away from the middle, and then to figure out how unusual that is, we find a p-value. And the p-value in a spreadsheet, if it's a left tail, is just going to be the t-dist, t.dist. And the t.dist wants to know what is your t-score, this guy up here, what are your degrees of freedom, and then it wants a true after. So this right here is the left tail, left p-value. The right p-value, we have to do a 1, oh wait, we don't have to do 1 minus because there is a right tail formula, like the normal. That would be t.dist dot right tail. And that's just whatever your t-score is and your degrees of freedom. Don't need a true there. And then there's the two-tail, and there is a two-tail version. That would be t.dist dot 2t, whatever the t-score is, comma degrees of freedom. There is a slight catch on this one I mentioned last class or the class before. In the, let's see, in both the right tail and two tail, they expect the t to be a positive number. So if you think you're doing a right tail but you get a negative t, something's wrong with that situation. So either you don't have a right tail or you made a mistake in calculating the t-score. If you're doing a two tail and you get an error when you plug it in, it's just because you happen to have a t on the left side, but the computer wanted it to be a positive number. So just throw in a little opposite if you get an error there. And you might remember before, I often say to get a two-tail p-value, find either the left tail or right tail as appropriate, depending on which side of your data falls on, and then just double it instead of using this formula. So let's go try. So we're going to do a confidence interval for some data, and then we'll do a hypothesis test. So this is the summary of difference in for two means independent population.